So I'll try to go as quickly as I can through some of the sort of theoretical linear algebra that's at the basic background of this. We want to think about the, our ultimate goal at the moment is to understand the fx module v with respect to an endomorphism T which goes from V to V, right? So remember basically the way that acts was f of x acts on a vector v by the corresponding polynomial in T acting as an operator in V. So, what that means in particular is that, for example, if I had f of x equal to x squared plus 2x minus 1, and I let f of x act on V in the vector space generated in the fx module generated by T, I would look at T squared plus 2 times T minus the identity operator acting on V. And what that would specifically mean is T of TV plus 2 times T of V minus V. That's explicitly what the operator, what the vector is that f of x dot v maps to if f of x is x squared plus 2x minus 1. Right.
Okay, so you're taking this function t, and we're creating a vector in this V vector space?
Yeah, so
okay.
So V is the vector space, T is linear transformation from V to V, and our goal is to understand the structure of the linear transformation T by examining this very somewhat abstract fx module built from the linear transformation.
Yeah, but in particular it's a polynomial. Okay.
Right, well, so fx is a set of that is polynomials with field coefficients. And so that is it is a module over the principal ideal domain of the polynomial ring of the field.
Oh, okay, that makes sense because T of V gives you V again, so you can just redo
Yeah, so here R is equal to fx, and the module is the vector space over F. And T appears in the module action, right?
Yeah.
So there's some theorems I should share with you. Theorem. Well, the one is the Kayla-Hamilton theorem. And I'm putting these things terribly out of order, okay? But Kayla-Hamilton theorem basically says that if you say f of x is equal to the determinant of, let's see here, x times the identity minus t, right? Or you could just write it as x minus t if you wanted. This is a, so the dimension of V, I'm going to assume is n, right? N-dimensional vector space, finite dimensional. So the Kayla-Hamilton theorem says that this is the so-called characteristic polynomial of T. All right. It's the determinant of an operator on n order vector space, which means that it's the determinant of the matrix of the operator with respect to any choice of basis you like, which is an n by n matrix. So this is its nth order. So if your linear transformation is on a 5-dimensional vector space, your characteristic polynomial is 5th order.
Yeah.
And the Kayla-Hamilton theorem says that f of t is 0. So if you plug the linear operator into its own characteristic polynomial, you get 0. It's Kayla Hamilton theorem.
So like, I can kind of see like maybe like application-wise, like what we're trying to actually do is apply like polynomials over a vector space, because you can't really do that straight up due to the fact that like you can only have scalar multiplication, right? And so we're using composition of functions to actually like create these.
Yeah, we want to leverage polynomial algebra
On
to
vector
gain
spaces.
insight into vector spaces. That's what this
Yes.
module does.
Okay.
That is exactly what this module does.
Okay.
Okay, so the other thing that I should mention, there are many things I should mention. Another thing that is important is the concept of a minimal polynomial. So the minimal polynomial, let's say m sub t of x, right? Element of f of x is monic polynomial of smallest degree for which m sub t, and we'll drop the t, all right?
Yeah.
Let's just say m of t is equal to 0. So that means that the characteristic polynomial is, of course, in the running for being a minimal polynomial. But it's not usually the case that the characteristic polynomial is equal to the minimal polynomial. Often there's a polynomial of lesser degree, which will serve as the minimal polynomial. The minimal polynomial serves as the annihilator for the fx module.
Is it because it's equal to 0? So like when you multiply by stuff.
So what's the definition of the annihilator of a module? So let's remember. Maybe not remember, maybe introduce for the first time, right? I keep talking about it, but I never write it down. I don't know if I did. But we can look it up, right? I mean, I'll just pick up my copy of Dummett and Foote, which I have left an hour drive in a Easter locked building away from here. You got it?
I don't know.
Oh, you're just guessing.
This is dominant foot.
Yes, I know, but I was like, are you open to the,
Oh, no. I'm not that level good.
so I'm looking for annihilator. One of my favorite mathematical words. You know, annihilator. 249, maybe 434. Here it is. Well, here's the annihilator of n. It's all right. So it's a subset of the ring that kills everything in the module. So the annihilator of m, all right, will be equal to f of x in polynomials over f, right? Such that f of x dot v equals to 0 for all v in the vector space.
Oh. It's the 0 scalar.
That's right. So what that means, right,
Yeah.
is that yeah, that means that this, of course, this means that f of t acting on v is equal to 0 for all v, right? Which means that f of t is equal to the 0 operator, right? The 0 operator on v. So certainly the minimal polynomial is in there. But it's better than that. The minimal polynomial generates it.
Okay, so all, okay, yeah. Gotcha.
See, if anything, I mean, this is literally generated by m of x.
Mhm.
Because any multiple of this, polynomial multiple of this, will then, through the rules of polynomial,
It's like zero divisor. Like you can take scalars as zero divisors and they're still,
Right.
they're
So
still
if you-
zero divisor.
well, I mean, just here, if we have m of x times g of x, right,
Mm-hmm.
and we let that act on v, we get m of t, g of t, but this means composition,
Yeah.
right? I mean,
So that's, yeah.
so,
M of t, or m of g, t on v.
right. So these commute,
Yeah.
and so you get g of t,
Or so it'd be zero or, oh, okay.
m of t and v, but that's the zero operator. So
Yeah, this is zero.
And so that shows you any multiple of the minimal polynomial is in the annihilator, but you can also use the fact that this is the polynomial of least degree for which m of t equals to 0 to see that that has to be the generator for it. You know? Okay, so in any event, finding the minimal polynomial, it goes a long way to describing the fx module built from the linear transformation, because remember that the annihilator of m, this is the notation was, this is the a sub m
Mm-hmm.
in the invariant factor list. A sub m is the annihilator, well, I should say the ideal generated by a sub m is this is an ideal of the module. The ideal generated by the annihilator is the generator of the annihilator ideal is the a sub m. It's the, you know, in the a1 divides a2 divides a sub m, it is the last invariant factor. And all of the invariant factors that came before it have to be divided. All right. There are other theorems which are known about the Kayla-Hamilton, about the characteristic polynomial and about the minimal polynomial, which you should be aware of. Another important theorem to know is that any root of the characteristic polynomial
Mm-hmm.
will also be shared by the minimal polynomial. So if you've got a factor of x minus 1 in that,
Mm-hmm.
there's an x minus 1 in this.
Okay.
If there's an x minus 1 cubed, there might be an x minus 1, an x minus 1 squared, or an x minus 1 cubed in the middle. It depends on the details of the map. Calculating the Smith normal form of the matrix of the map over the ring fx
Yeah.
will allow us to figure out which one it is. So, like, basically, the Smith normal calculation allows you to calculate the minimal polynomial with a big old nasty matrix calculation. It's probably not the smartest way to do it.
Mm-hmm.
Like, this is of theoretical interest more than it is of computational interest, I believe. But maybe that's just because I'm not good enough at the Smith normal form yet. I don't know. All right. What else can I tell you? Let's see here. So, let me tell you a little bit more about the rational canonical form before I get into the Smith normal form stuff. So what is rational? Oh, come on. Rational canonical form. If we have p of x equals x to the power d minus alpha d to the minus 1, x to the d minus 1, minus minus alpha. So I put minuses here because I want pluses somewhere else, okay? I don't know. Because I'm following something, probably Curtis, maybe Rotman, I forget. So if this is a polynomial in fx, right?
Mm-hmm.
And that language I don't remember. And P of X is an order. Sorry, Patrick, I don't have the book to, I feel like this is from Curtis's linear algebra.
I do have that book, but that is also an hour drive away.
Yeah. Is an quote unquote an order of Lingle, V, Wrangle. Then the matrix of T, maybe we can make sense of it from what follows, okay? Matrix of T restricted to Lingle, V, Wrangle, is A, some introducing notation here, A sub Tx equal to zeros on the top row, all the way until you get to alpha naught. And then the last column you get alpha naught, alpha 1, alpha t minus 1. And then you got ones on the subdiagonal. So ones on the subdiagonal, zeros elsewhere. Zeros elsewhere. This is called the companion matrix of a prime polynomial P of X. I think it's really just the companion matrix of P of X. But it's more interesting in Curtis if it's a prime polynomial. Remark, even if f of x is not prime, if f of x is the order of Lingle, x, Wrangle, then ft of x equals to 0, and if it's monic, then that is defined with respect to that basis, and we'll still find. Anyway, so basically my remark on this page says, hey, this still makes sense if it's not prime. Now, what is order? Order. Goodness. So, maybe we'll make sense of it. Yeah, the basis with which this operator is the matrix, as this matrix is beta is equal to V, PV, T squared V, and T D minus 1. So I believe this order business means that P, T, V equal to 0. And not just that, I mean, it means this is equal to 0, and this is the smallest, the lowest monic polynomial such that this happens. So if you have so you're given a linear transformation, right? And you can hit it, with polynomials and linear transformation. Then there has to be a smallest polynomial of lowest order such that this is 0, and that's a monic polynomial.
So going back to down here, is it just the first annihilator?
So it's like the annihilator, but the concept for the annihilator is that so this if this was was a basis for all of V, then this would be the annihilator.
Okay.
But this doesn't have to be all of the vector space.
Just a subset.
Just a subset. This is the T cyclic basis. T cyclic basis generated by T, generated by V under T. There may or may not exist a T-cyclic basis for the entirety of your vector space for a given transformation. Now, yeah. So this though is once you, okay, so accepting the setup that there is, this polynomial gives you PT of V is 0, right? And P of X is that, right? If we look at, so this is the basis, right? So what is what's T of the first thing equal to? TV, right?
Yeah.
With that, I'll use the other notation as a means to separate them in our mind.
Yeah.
But the point is that that's the second basis element, right? That's why we have 0, 1, 0, 0, 0, 0.
Yeah.
Because this is the first, so this means that if we look at the coordinate, the coordinate vector of this with respect to the beta basis, what do we got? 0, 1, 0, right? And this goes on, right? Like, generally speaking, if we look at the, the jth power acting on V with respect to the beta coordinates, we get, of course, what? We get
The jth column.
e to the j plus 1, right? Because it goes to the next one, right?
Yeah.
But that's only true for j equals to 1, 2, all the way out to d minus 1, right? So there are d columns here in total. Yeah. Now what's interesting is what
D columns, but you missed the last column.
this is a square matrix.
Oh.
So 0 to d minus 1 is d things.
Yeah, but the amount of columns, like we were talking about this as columns, right?
Yeah, the number of columns equals the number of rows. It's a square matrix.
Okay.
The companion matrix is a square matrix.
Yeah. Gotcha.
So this boring story continues, this shifting
Mm-hmm.
all the way on up to here. Then at the dth one, something interesting happens. See, T of the dth power.
Gives you alpha d minus 1.
Yeah. Well, yeah. So I should say that. So really, what I really should talk about is T of T d minus 1, right? This is the dth basis vector right here, right?
Yeah.
See that? So the coordinate vector of this defines the dth column, but that's Td of V, right? Which is what? Well, then I have to go back up to here, right? See, P of TV is 0,
Yeah.
which means that T to the D acting on V is equal to all of this stuff. So it's equal to, alpha d minus 1, T d minus 1 acting on V, alpha 1t acting on V plus alpha naught times V, coordinate vector of that, with respect to this beta basis.
What do we
It would be minus, but we put minuses up here so that when we solve this for t to d acting on V, we get plus alphas acting on lower powers and t acting on V, which then straight up gives us the last column, see?
Mm-hmm.
See, so alpha naught is the first thing in the basis.
Yeah.
So the last shall be first, and then there's an alpha 1, all the way down to alpha d minus 1. So the companion matrix for a transformation is something that you can write if you have a subspace, right? If you have a subspace of the vector space which permits a t-cyclic basis, then the matrix of the transformation with respect to that subspace, if you will be a companion matrix. And also, this is one of those invariant subspaces that we talked about a few weeks ago. Did you see why this would be an invariant? So like if we define W equal to, you know, if W equals to this thing, W equals to the thing generated by V, right? We could also point out is the annihilator of what? It's really the annihilator of P of T, isn't it?
Mm-hmm.
I guess I can't quite say that. There might be other things that are, maybe this is bigger than that, but anyway, that aside, this is definitely going to be a subset of this. For sure it's a subset of the annihilator. Because this is everything in the vector space which P of T kills. My point to you is that this is definitely a T invariant subspace, because if you let T act on this, you're just back where you started again. So this is a T invariant subspace, which means it's one of those, it gives you a submodule of the fx module. And the primary decomposition theorem gives us that the finitely generated fx module can be written as a direct sum decomposition of submodules.
Mm-hmm.
This is going to be one of those.
Okay.
Okay, so just to give you some more concrete examples here of companion matrices, and this by the way, you've seen in differential equations. Remember when you take an nth order problem and you reduce it to a system of first order problems?
Yeah.
With the usual like y prime equals to x1, y prime prime is x2, y prime prime is x3, and so forth and so on down the list.
Yeah.
That will give you a matrix like this, where the last one is what picks up on the structure of the nth order differential equation, because that's the one that relates the x1 through xn, which correspond to the y primes through y n minus 1 derivatives. So something like that. My counting's probably a little bit off, but so here's a simple example. If you have p of x is x squared plus 1, this gives you the companion matrix 0, minus 1, 1, 0. If your polynomial is x squared minus 2, that gives you the companion matrix 0, 2, 1, 0, right? And finally a bigger one. If you have p of x is x cubed minus 2, then that gives you 0, 1, 0, 0, 0, 1, and then you get 2 up here, and 0 is down here. So these are companion matrices. Yeah, this is definitely from Curtis. sure I want to write all that. Okay, fine. I guess I need to write a little more. So the issue I was just quibbling over is like, what if there's more? It's a thing. Let me just rather than tell you what, rather than doing the full theorem here, let me just give you an example how it works.
Alright.
Aldrich, are you staying here with Papa?
Yeah, I can. That's part of the deal. I mean, Dr. Agree as well.
That's part of the terms and conditions of this study today. So. I think that's a pretty big deal. So if he's like, I'll try to write the lemma without writing too much, but if you have cyclic subspace, Langle V, Wrangle, with order P of X to the power E, then
What's E?
so E is the, let's see here, I don't know what the name, I think he calls it the exponent. P of X is a prime polynomial for Curtis,
Okay.
and I think E is the order.
Okay.
It's a positive integer E, I can tell you that. Then you can make your basis for V look like, what you do is P of T to the E minus 1 acting on V, all the way up to T to the D minus 1 P of T acting on E to the minus 1 V, and then that just keeps going until eventually it gets to V, T, V to that, T to the D minus 1 V. I know it's kind of a mess. So you're cycling through like the next to highest power of this. Like this is automatically 0. When he says order P of X T, what he means is that Px to the power E acting on V is, P of T to the power E acting on V, which is 0. So it's the So if in the field you're working over, it's possible to write your polynomial as a prime polynomial repeated, all right? So like, instead of having x squared plus 1, you might have x squared plus 1 squared as the thing that kills the vector. Then you can use this as your basis, and then the matrix of T restricted to that basis looks like A, B, 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 A is down the diagonal, where A is equal to APX, which is D by D, and B is a matrix of all zeros except for 1 in the top rightmost upper component, and everything else is 0. So this is what, in Curtis's view, the rational canonical form looks like for a repeated polynomial. So just to let me be specific here. So if you had like if you had x squared plus 1 squared, all right, then this would give you, I got you, our a from example 1 on the diagonal blocks, and 1 up here. So, vice versa, if you look at this matrix, you go, oh, I know that that is a matrix such, and by the way, it's kind of annoying, where's V in all this? Like if you look at the BV bases, V doesn't appear in a nice spot, it's like D from the last one.
Yeah.
So I think in looking at this, I've got E equals to 2 and D equals to 2. So this would make my V, quote unquote, if I want to think about it directly in terms of like just the standard basis being a V. I think this would have E, I think E4 would be my V, because that's like, the list would be, I think, let me just write it out. If I'm not wrong, it would be x squared, I need to use t, right? So t squared plus 1 v, right? Comma t of t squared plus 1 v, comma v, comma tv. That would be what that becomes in this example, which is my example 4. Does that make sense? So this is, let's call this A, right? So if I'm right, AE4 should be what? It should be, well, it should be TV, but that's like, I guess that's a kind of a self-fulfilling prophecy. AE4 is 1, 0, minus 1, 0. Which is this.
I thought V would be 0, 0, 1. 0, 0, 0, 1. Unless you're going by rows.
V would be what? 0, 0, 0, 1?
Yeah. Because TVs. So yeah, so A times E4 would be, yeah, you get the 1 there. That should be 0, minus 1. Yeah, I don't know. Alright, I'm okay, so there's like, when I'm more comfortable with the Jordan form. Mm-hmm.
So if you have something in Jordan form, then you can say something nice and simple, like the standard basis is a Jordan basis for the Jordan form.
Mm-hmm.
It may well be that the standard basis is a cyclic basis for the rational canonical form. That's what I'm trying to decide for myself at the moment. Now, so like a squared, so a squared plus the identity acting on V, that should decide what the first column is. See, because like the matrix of T, the first column of the matrix of T should come from T acting on the first thing in the basis. All right, and so when I convert over to the matrix, I have to look at, this becomes a squared plus I acting on V. We decided V was E4. If I think that comes from, well, I gotta be careful. Wait a minute, no, T of V is E4.
I thought you were meaning E4 is the column vector 0, 0, 0, 1.
Yeah.
So that would be T of V.
Yeah. I'm sorry, I think I feel like I'm wasting your time. So like this, when I square this matrix,
Yeah.
I get -1. Sorry, I'll think of this. You get -1, so this get a squared, it gives me -1, -1, -1, -1, I believe, for the diagonals. Wow. Hold on a second. Oh, yeah, nice one. Yeah, nice one. No, I don't know what happened. Let me think about this here. This one. I think that's 0. Oh. Hey, let me not try to do this right now. I don't have enough space here to do it justice anyway. Oh, so this is the matrix that you get for thinking of it this way in Curtis, but if you just squared this out, so I'm giving up on my previous conversation, sorry. Being lazy. We get that, right? So what's this would be, I mean, these are different matrices, right? So, or do we, did I do that right? Alpha d minus 1. No, I should have 0 here, right? Yeah. So, because I do the minus the constant, minus the linear, there's no linear, minus the quadratic, and then minus the next to leading order, which here is cubic. So this is the companion matrix of that. Okay? So this would be the matrix of, with respect to the t-cyclic basis of the form, like we had over there, V, TV, t squared V, t to the d minus 1 V. Right? This one is easier to think through. Let me just talk about that for a second, to redeem myself. So this, why Curtis does this, you have to look at Curtis, okay? Maybe we'll be able to say more about that as we go on, but so this here, I believe this makes the standard basis that kind of t-cyclic basis. So like A1 equals E2, right? A2 equals E3. AE3 equals E4. AE4 equals to, well, minus E1 minus 2E3, right? But, so I think you can say that V is equal to E1, right? So T of V is what? So I'm thinking of T is equal to the left multiplication by A, all right? Here. That's the correspondence between linear transformation and the matrix, which is left multiplication by matrix. So T of V is A1, which is E2, right? And T squared of V is T of E2, which is E3, right? And T cubed of V is T of E3, which, by the way, is, minus E1 minus 2E3. In other words, T cubed V plus 2E3 was what? Was T squared V plus E1 was V equal to T cubed plus, I should have. Why did they do? Did I do it right? I don't think I did it right. Sorry. Oh, sorry, I got confused all of a sudden. E1 is V, E2 is TV, T squared V is E3, T cubed V is T cubed, that's E4, my bad, E4, yeah. And then finally, what's T, and then this is what's sort of interesting, T to the fourth V is what?
Minus
T of E4, right?
Yeah.
So that's AE4, which is also equal to minus E1 minus 2E3, but what is that equal to? That's minus V. E3 was what? Was T squared, so minus 2 T squared V. So to put that all together, you've got T to the fourth plus 2T squared plus 1 acting on V equal to 0. So what I'm trying to say, and it's taking my sweet time saying it, is that for a companion matrix, the standard basis is a cyclic basis with respect to the left multiplication by A operator. So if you want to know what's the minimal polynomial for, so I define minimal polynomial for transformation, but we can just as well define minimal polynomial for a matrix, right? It's the polynomial of smallest order, monic polynomial of smallest order, that when we plug the matrix in the polynomial, we get zero matrix. And so the minimal polynomial for the companion matrix will be the matrix, it will be the function, it will be the polynomial for which the matrix is the companion. Is that true though? See, is that true here? Or in fact, is the minimal polynomial for this matrix actually just x squared plus 1? See, this was x squared plus 1 squared, right?
Yeah.
So the question is this is the minimal polynomial for this that? Or is it actually x squared plus 1?
That would be 0.
Yeah, we should just, why don't we square this matrix,
Yeah.
right? That's the way to decide. So we gotta take 0, 1, 0, 0, 1, minus 1, 0, minus 2, 0. And I'm gonna write it down again because I'm too dumb to not. Is that lightning?
Maybe.
So there's a squared, right?
Okay, so 1.
I got
0.
You got 1?
That column times that matrix. Oh, I understand. Yeah, that's 0. Times 2. That's 1, right? Yeah. Oh, 0. This column times this is 0. This column times this is 0. And then you get 1. This column times this one is 0. And then you get this column times this column times this is 0. This column times this one is 0. This column times this one. This column is 1. This column 0. Wait. Minus 1. Minus 1. 0. Minus 2. 0. And then this column times. That's 0. This is minus 1.
Right, so
This is 0. And this is. This times. This times. Oh, yes, minus 2.
so I think at this point
Yeah.
it's clear that a squared plus the 4x4 identity matrix is not equal to the 0 matrix, right? Because if you added, you know, the identity matrix to this, you don't.
Yeah.
So apparently no. Good. Okay. Now. Now there is an advantage of looking at it in terms of the matrix I erased versus this one. But I think that's the distinction between like Curtis and say, I don't think that Dunn and Foote does the thing I erased. I think that's from Curtis. Anyway, let me tell you where we're going with all this, okay? So what's the rational canonical form? So if you have T from B to B, and you have elementary divisors P1 of x to the E1, PR of x to the ER, and repeats are possible. Then your matrix using the basis like we had here repeatedly, each one of these will give you a matrix of the form like C1, C2, CR, which is the direct sum of these matrices, yeah? So it's a block diagonal decomposition of the matrix, where each one of these blocks is coming from as the companion matrix of these repeated prime factors. This is Curtis's way of doing it. Now, I think in Thumb and Foot, what you just do is, I think you just find the, well, let's do it. I'm trying to think of the words. But I don't think you do this, well, I know you don't do this. I don't think he does this. Anyway, let me. All right. So the interesting thing about all this, of course, is that you can take two matrices, right? And you can do the calculation I'm about to show you. You can find the rational canonical form for those two different matrices. And if they have the same rational canonical form, then they're similar matrices. Which means that it's essentially the same linear transformation looked at from a different choice of basis. Like we proved the other day, right? Like,
Yeah.
Okay, so Smith normal. So what I was trying to explain to you here is basically that the polynomials that we're trying to derive, they're essentially the order for particular cyclic subspaces. They end up being something that will kill like a piece of the vector space. And then if you write the totality, your total basis in terms of, each one of these cyclic subbases, then the matrix for the transformation then will be a block diagonal decomposition where each one of the blocks is the companion matrix for one of those factors. We'll eventually get the marker off the board. Now, personally, I'm much more a fan of the Jordan decomposition, but the downside of the Jordan decomposition is it's with respect to the eigenvalues. And so the eigenvalues are the roots of the characteristic polynomial.
Yeah, I remember right before the GRE, it's you essentially replace the diagonals with minus that number minus some eigenvalue and
Right.
take a determinant of it.
Right.
Fortunately, I did not have to do any of this calculation.
Oh,
We got to do it though.
You got it. Well, maybe they'll decide to be civilized and actually give you guys a second chance at the GRE this year. Who knows?
It's just a myth right now. I really doubt they would miss out on money.
So the rational canonical form doesn't require roots for the characteristic polynomial.
Yeah.
It's just if you can factor the characteristic polynomial over your field, then there's a corresponding decomposition of the transformation in terms of T-cyclic subbases. But over the rational numbers, we can have irreducible polynomials over arbitrarily high degree, and